let's apply what we have learned to different atoms and try to write what we say an orbital filling diagram for these atoms. Let's start from the periodic table. Let's draw the periodic table first. And small and easy sketch of the periodic table. And let's start from the simplest element in the periodic table, which is hydrogen. Hydrogen has one proton, no neutrons, so its mass number is also 1. Starting with the number of protons, neutrons, and electrons in hydrogen, it has one proton, one electron in the neutral atom, and it has 0 neutrons. We start drawing the orbital diagram starting from the lowest energy level, n equal to 1. And in the first energy level, there's only one sublevel, 1s, with the s orbital, and the single electron in hydrogen sits in this s orbital of the first energy level. Here's the orbital diagram of hydrogen. The electron configuration shows the orbital diagram in a more simple way. It shows the energy level, it shows the sublevel, S, and it shows the single electron in the hydrogen as 1s1. We call this way of showing the electron, the energy level, and the sublevel an electron configuration. On the other hand, the other diagram that we have drawn showing the energy level with the electron, arrow upward, the arrow upward showing the spin as clockwise, this is the orbital diagram of hydrogen. Now let's pass on to the next element in the periodic table, which is helium, on the very right side of the periodic table. Helium, having an atomic number of 2 and a mass number of 4, has 2 protons, in the neutral atom 2 electrons, and 2 neutrons. Right now, we are interested in the 2 electrons in helium, and we're going to draw the orbital diagram for helium. We again start from the lowest energy level according to Aufbau principle, n equals to 1. The first energy level is made of one sublevel, the s sublevel, and the s orbital, 1s. The 2 electrons in helium go into the 1s orbitals, one up, one down, one arrow up, one arrow down, showing the clockwise and the counterclockwise rotation of these electrons. The electron configuration for this atom is first energy level, 1s, 2. Finished. We can see that in the helium atom, the first energy level is completely filled. And S2 means, S2 shows that the orbital, s orbital, has a spherical shape and the 2 electrons are moving in the s orbital in any direction, but in a balanced, symmetrical way. S2 shows spherical symmetry. Now let's look at the previous atom, which is hydrogen. In the previous atom, the s orbital, which is a spherical orbital, is filled with 1 electron, and it is moving in all directions also. And because this orbital itself is spherical, we can say that the S1 hydrogen has spherical symmetry also. In simple words, spherical symmetry means that the electrons are distributed within any sublevel in a symmetrical way, making the atom and its orbitals balanced. Now let's pass to the next element in the periodic table with the atomic number 3, lithium. Lithium has 3 protons. Its mass number is 7, so it has 4 neutrons And in the neutral atom of lithium, it has 3 electrons. Let's place these 3 electrons in the orbitals. In the first energy level, n equals to 1, and 1s orbital, we put 2 electrons, one up, one down, one clockwise, one counterclockwise. Then we pass to the next energy level, which is n equal to 2. In n equal to 2, the lowest energy orbital is the 2s orbital, and the third electron in lithium sits in that orbital either clockwise or counterclockwise. So this is the orbital diagram for lithium. From this orbital diagram, we can draw the electron configuration, which is 1s2, 2s1. Again, if we look at the orbitals in lithium, they are both s orbitals, which are spherical orbitals, so we say that lithium has spherical symmetry. We can also analyze lithium in terms of unpaired electrons, number of unpaired electrons. In the first energy level, the electrons are already paired. But in the second energy level, in 2s, we have a single electron which is unpaired. Being unpaired gives a bonding ability to lithium. Or we can say it can react more easily because of this unpaired electron in the 2s orbital. So we can say lithium has one unpaired electron. We will talk about the unpaired electrons more in the coming topics. Now let's pass on to the next element, which has an atomic number of 4, and beryllium. Beryllium has 4 protons, 4 electrons in the neutral atom, and beryllium's mass number is 9, so it has 5 neutrons. The orbital diagram, n equals to 1, is 1s, 2, 2s, n equal to 2, 2s, 2. 4 electrons are filled in. So electron configuration is 1s2, 2s2. When we look at beryllium, we can say that it has spherical symmetry because the s sublevels are filled. It has no unpaired electrons. Skipping a few elements in the periodic table, let's start filling in the orbital diagram for carbon. Carbon has 6 protons and 6 neutrons, making its mass number 12. 6 protons, 6 electrons, and 6 neutrons. The orbital diagram for carbon is n equal to 1, 1s, 2 electrons. In n equal to 2, 2s, 2 electrons. And then there are 2 more electrons we should be filling in. So they go into the T2p sublevel, px, py, pz. 2 electrons, 1 in each orbital, either clockwise or counterclockwise. This is the orbital diagram for carbon. The electron configuration for carbon is 1s, 2 electrons, 2s, 2 electrons. In the 2p orbitals, we can say that it has 2p, 2 electrons. We have put 1 electron into each equal energy p orbitals. P orbitals have equal energy and more energy than the s orbitals. We have put in 1 electron. Then, if we need to put in more, we're going to pair them up later on. This is called the Hund's rule. Hund's rule, again, says that when filling in equal energy orbitals like px, py, pz, or the 5d orbitals or the f orbitals, we put 1 electron into each orbital and then pair them up. So we have written the electron configuration for carbon. we can see that carbon has two unpaired electrons. And let's see whether it has spherical symmetry. Yes, the 1s orbitals are spherical. The 2s orbitals are spherical. But when we look at the 2p orbitals, we can see that there are only 2 electrons in the 2p orbitals. And this makes an unbalanced electron population in the 2p, and it makes the symmetry destroyed. So we can say that carbon does not have spherical symmetry. We can show this unbalanced or unsymmetrical situation by drawing the p orbitals in carbon. Along the y-axis, we have 2 lobes of p orbitals. Along the x-axis, 2 lobes. And along the z-axis, we have, again, 2 lobes. Now, imagine that we are putting 2 electrons in the p orbitals. One of those 2 electrons goes to px. Here is the px, one of the 2 electrons. And this electron is going to move in any direction with high speed in these 2 lobes of electrons, px. There is an electron in the py also. Here is the electron, and it's going to move along the y-axis in these 2 lobes with high speed. There is no electron in the pz orbital. So this pz orbital is going to stay without any electrons. You can see that the situation in carbon is an unbalanced situation where the symmetry is destroyed. In that case, we can say that carbon does not have spherical symmetry. What can be done to make it have spherical symmetry? Maybe if there was another single electron in the pz orbital, it would have spherical symmetry, as we can show in the diagram. But carbon doesn't have this electron in the pz, so it doesn't have spherical symmetry. The next element is nitrogen. Now, I'm putting nitrogen here so that I can show you that it has spherical symmetry with the 3 orbitals px, py, and bz being half filled. Nitrogen has 7 protons. In the neutral atom, it has 7 electrons also, and its mass number is 14, so it has 7 neutrons. Its orbital diagram is n equal to 1, 1s, 2 electrons, n equals to 2, 2s, 2 electrons. Then, in the same second energy level, the 2 p's, px, py, pz, 2 p's, 1 electron is put in each to fill up the 7 electrons. So, nitrogen has 3 unpaired electrons, but because of the equal or even distribution of electrons in the p orbitals, as we can see in the diagram here, it has spherical symmetry. Now we can make a summary of spherical symmetry. Which kinds of combinations of orbital electron filling can have spherical symmetry? When